Hello everyone, my name is Byung Lee from Seoul National University. In this presentation, I want to share our work Continual Multiple Instance Learning with Enhanced Localization for Histopathological whole slide image analysis, which will be presented in ICCV25. I will briefly introduce whole slide image analysis and multiple instance learning, and then explain the contribution of this work. Histopathological whole slide image is a gigapixel scan of glass slide that contains stained tissue section. Due to its very high resolution, pathologists can view and zoom into these images on screens similar to how they use the microscope. Recent advances in deep learning for medical imaging have also revolutionized the whole slide image analysis towards automated diagnosis, prognosis, and therapeutic response prediction. However, deep learning-based whole slide image analysis have several challenges. First, it often requires manual annotation of gigapixel images, which is time-consuming and labor-intensive. Second, processing every pixel of a whole slide image with a deep learning model requires substantial computational resources. Furthermore, local fine features are usually critical for diagnosis in whole slide image, so it prevents the use of downsampling. To address these challenges, multiple instance learning, or MIL, has been proposed for whole slide image analysis. Instead of processing every single pixel in the gigapixel image, MIL treats a whole slide image as a bag of small patches. So first, we extract patches from the whole slide image, and each patch is then processed to obtain its feature through a frozen patch encoding model. After that, these patch level features are aggregated, and finally, a collective decision is made at the slide level. The key advantage is that MIL leverages only slide level weak labels rather than pixel level annotations, and train only the model for aggregation into the slide level features. This greatly reduces labeling effort and significantly improves computational efficiency. So MIL allows us to analyze extremely large whole slide image analysis images effectively without requiring exhaustive manual annotation or massive computation. While MIL has shown promise for whole slide image analysis, its continual adaptation with minimum forgetting is also a critical factor for practicality. Recent work called Continual has already attempted to address this issue. However, in terms of localization for diagnosis, it still suffers from forgetting of previously learned tasks. To tackle this limitation, we propose our approach, COMO, which stands for Continual Multiple Instance Learning with Enhanced Localization. As illustrated here, compared to Continual, COMO preserves localization ability across tasks, significantly mitigating the forgetting problem. Here is the overview of our proposed framework COMO. It consists of three main components. First, the grouped double attention transformer, or GDAT, re-embeds patch features and improves discriminative power of extracted patch features with efficient attention mechanism. Second, the back prototype space pseudo-labeling, or BPPL, generates prototypes to enhance localization and guide both slide level prediction and patch level localization. Finally, the orthogonal weighted low-rank adaptation, or LoRa, allows continual adaptation of closed tasks while minimizing forgetting without storing any previous data. Let me explain grouped double attention transformer, or GDAT, first. The main goal of GDAT is to reduce the high computational cost of standard attention, since more than 10,000 of patch tokens are involved in attention for whole slide image, which is computationally expensive. So instead of directly applying full sample attention, we replace it with two sequential attention steps. Concretely, we first compute queries and keys from grouped features, which significantly reduces the number of tokens to compute, and then apply attention in a hierarchical manner. As shown in the equation, this sequential design reduces the original quadratic complexity from all large M scales, where large M is the number of instances, down to O small m large M, where small m is the number of grouped features. This significantly improves efficiency, making it possible to process gigapixel whole-side images more effectively. This part introduces our back prototype space pseudo-labeling, or BPPL. The key idea is to assign pseudo-labels at the instance level by comparing features with backlet prototypes. So we start by aggregating patch features and obtaining attention weights. These attention scores are normalized and can be interpreted as class probabilities. Then we train to generate discriminative positive and negative prototypes with the separation loss. Based on the similarity between instances and prototypes, we adaptively select confident instances and reject uncertain ones according to the model's current status. This way, BPPL provides reliable pseudo-labels that guide the model towards better instance-level localizations. Specifically, the similarity between instances and prototypes is calculated, and a selection function determines which instances are used as pseudo-labeled samples. The selected instances contribute to the instance loss, while the back-level classification still supervises the over-prediction. Consequently, we combine three losses: the back classification loss, the instance-level pseudo-labeling loss, and the separation loss that encourages distinct prototypes. Together, this enables BPPL to refine both back and instance-level learning in a weakly supervised manner. Finally, we propose our LoRa, which stands for orthogonal weighted low-rank adaptation. The key idea is to introduce new learner weight bases that are enforced to be orthogonal to the bases learned in previous tasks. As shown in the figure, the first task weight is trained and then decomposed using single value decomposition. For subsequent tasks, our LoRa guides learning with two constraints. One is intra-orthogonality, which enforces independence among the bases within the same task. And the other is inter-orthogonality, which ensures that new bases are orthogonal to those from previous tasks. This design prevents interference between task and mitigates forgetting. As illustrated in the rank study on the right, our LoRa maintains the effective rank across tasks. And interestingly, we can observe that the effective rank required for learning new tasks becomes progressively smaller as additional tasks are introduced. Now, I want to present our results on forgetting under continually changing organs. In this setup, the model is trained sequentially from sentinel lymph nodes to liver, prostate, pancreas, and finally colon. The dataset statistics are summarized in the table on the right. As shown in the plots, when new tasks are introduced, conventional methods such as EWC or ER suffer from severe performance degradation on earlier tasks, indicating strong forgetting. Even Continual, which was designed for continual whole-side image analysis, still shows noticeable drops in localization accuracy. In contrast, our proposed COMEL consistently preserved performance across tasks, showing the least amount of forgetting and achieving results closer to the joint training upper bound. This is the qualitative results. The time row shows the ground truth instance labels. Here we zoom into a specific region for a closer comparison. If we look at the results of fine-tune and ER, we can see that the localization regions quickly deteriorates as more tasks are learned. Inflora alleviates this problem to some extent, but still fails to retain accurate localization, especially for river case. Consulate also struggles to preserve consistency across different organs. In contrast, our proposed COMEL maintains clear and accurate localization through all tasks, even after training on later organs such as pancreas and colon. This is the quantitative results. We reported instance-level accuracy, forgetting, IOU, and dice score for localization to detect tumor regions. We also measured the bank-level accuracy to evaluate the slide-level prediction, that is, the tumor slide classification. First, we can see that simple fine-tune suffers from severe forgetting, with poor IOU and dice score. Regularization-based and rehearsal-based methods shows some improvement, but still fall short in preventing the forgetting. LoRa-based approaches like Inflora shows better results, but their performance is still limited. In contrast, our proposed COMEL achieved the best results across all key metrics. Specifically, COMEL significantly reduced forgetting while achieving much higher IOU and dice scores. These results confirm that COMEL not only mitigates catastrophic forgetting, but also enhances localization in continual histopathology analysis. In conclusion, we propose COMEL, a framework for continual multiple instance learning with enhanced localization to address both classification and localization in whole-slide image analysis. Through extensive experiments on public whole-slide image datasets, COMEL outperformed priors in both classification and localization while minimizing forgetting under continual multiple instance learning setup. This is the end of the presentation. Thank you for listening.